is. Okay, so recall that a set S is compact if and only if every open cover of S permits a finite subcover. So what this means essentially is that if we have a whole bunch of open sets that are covering some set, and if we could take all of those sets and sort of throw away almost all of them and only keep a finite number of them and it still covers the set, then that would be considered to be compact. If that could happen for every single type of open cover. So first example, let's show you that an open interval in R is not compact. An open interval in R. And so for simplicity's sake, we'll just do the open interval 0 to 1. So let's look at an open number line. And let's put 0 and 1 on here. And we'll consider sets of the form, let's say AN equals the interval that goes from 1 over n to n minus 1 over n for n equals, let's see, I guess I can't start at 1 there. Let's see, 2 won't work either. So starting with n, so 3, 4, 5, etc. Okay, so when n equals 3, this would be the interval that goes from 1/3 to 2/3, right? So it would look kind of like this. And then when n equals 4, it would be equal to 1/4, 3/4. So it would go like this, etc., etc., etc. Now, as you can see, if I were to take all of these sets and union them up, all infinitely many of these sets from 3 on from 3 on, you could see that this would cover the whole space, the open interval from 0 to 1. However, no finite number of these would cover the open interval from 0 to 1, because if you stopped at any finite number, you would be missing parts that we needed as we extended towards infinity. So this is an open cover of 0, 1 that does not yield a finite subcover, demonstrating that this open interval is not compact. But an argument like this would work for any open interval. Just have it zoom in towards the sides with open intervals, with open endpoints, and it would not quite cover the entire space. Okay, so why don't we try an example that is compact, and I'll try to explain why it is compact. It turns out a closed interval in R is compact. This is, of course, the Heine-Borel theorem, is that a closed interval that's bounded, sorry, it has to be closed and bounded, would be compact. But if we take an interval, that's certainly going to be bounded. So let's just draw ourselves a quick picture here. And we'll let this one go from 0 to 1. And since the statement of compactness is for all open covers, what I'm going to do here is I'm not going to give a proof that this particular closed interval is compact, but I'm going to explain why sets that what we saw in the previous example won't work here to show that this is not compact. So recall that our ANs from before were equal to intervals that were extending from 1 over n to n minus 1 over n for n equals 3, 4, 5, and so on. So we were getting these kind of little open intervals. But notice that if we take all of these off towards infinity, right, if we take all of them for 3 on, it's never going to cover the complete interval. You're always going to be missing those endpoints located at 0 and at 1. So in order to have an open cover of this closed interval, we would have to have an open set included that it had 1 in it, so maybe something off the edge like that. And we would have to have an open set that would cover 0, so it would look something like that. Now notice that those two open sets that I put on the edges do cover part of the interior of the closed interval from 0 to 1. So therefore, those little pieces, those little overlaps, mean that we could find an open finite subcover by simply taking the two orange sets that I included there to get the endpoints 0 and 1, and then only taking finitely many of those red intervals until such a time that they extended past the orange on both edges. So there'd only be finitely many of those plus the two that we had on the edges, and that would show that we could cover this whole interval with these finitely many open sets. Now keep in mind, this is not a proof that this closed interval is compact, because in order for us to do that, we would have to take an arbitrary open cover. And this was a specific type of open cover, but hopefully that gives you a little bit of an insight into seeing why compactness is true about closed intervals and why it's not true about open intervals.